Hi guys, and welcome to the Year 10 Science video series on motion and forces, and this is video number 6, looking at Newton's third law. Now we've been having a look at Newton's laws, the laws that Isaac Newton used to describe motion, and also particularly for the types of interactions that occur when forces are applied to certain objects. And in this video, we're going to look at the third of Newton's laws, which states, it's probably the most well-known of the three laws, that for every action force, there is an equal and opposite reaction force. For every action, there's an equal and opposite reaction. It's the kind of colloquial version of this one, and it's very well known by that kind of statement. And so this is actually a law that involves two forces. So if you recall, the first law was basically about no force acting. The second law was about what happens when we have one resultant force. And from that resultant force, we get the equation F equals ma. And so now we're looking at the third law, and we're looking at forces in pairs. Two forces, equal and opposite. Okay, and these are often also referred to as reaction pairs. So there's lots of situations where we can invoke Newton's third law to explain what is going on. So probably the simplest one, and one of the examples that comes up a lot when you're looking at Newton's third law is like rocket ships. So if you were to blow up a balloon and then let it go, it flies around the room. But why does it fly around the room? Well, because the balloon is open, air is forced backwards. So air actually goes out of the balloon, and the balloon is propelled forwards by another force. So air is going out the back, and the actual balloon itself is moving forward. What we say about these two forces is that they are equal in magnitude and opposite in direction. Now, they don't necessarily cause the same acceleration. Whilst the force, the action force, is equal to the reaction force, it's not true necessarily to say that the action acceleration is equal to the reaction acceleration. This may not be the case, and it's dependent on mass. And we'll have a look at some examples of this later in this video. So when we are invoking Newton's third law, what we're looking for are action and reaction pairs. Okay, so two forces which are going to be equal and opposite. So if you like, in this case, the action force is the rubber of the balloon contracting and pushing the air backwards, so a force of air moving backwards. And then the reaction force is the force of air pushing forwards on the inside of the balloon. And these two forces will be equal. Force action and force reaction will be equal in magnitude, but opposite in direction. Now, of course, the thing that we need to remember is that despite the fact that the two forces are equal, and you can see on the diagram over here, and if I just change colors for a second, you can see on the diagram over here, this is the reaction force here. This is the action force here, the force action. And this one is the reaction, force reaction. Now, the two forces are equal, okay? So these two girls are on roller skates, and roller skates are chosen basically because that's going to reduce the frictional contact. So that's going to be something that's pretty good. But what you will notice is that girl A has more mass than girl B. So therefore, if the two forces are equal, if FA equals FB, and I might just change color again because I'm not sure how easy that green is to see, then acceleration A is equal to FA on MA, and acceleration B is equal to FB on MB. Now these two we've just said are the same, but because B has less mass, so B here you can see has less mass, then B's mass is smaller, so therefore the acceleration, because this is small, acceleration must be larger. So B must accelerate off in this direction quicker, or at least increase her speed quicker than A does in the opposite direction. The important thing here is that these are not sum to zero forces, okay? The forces do not cancel one another out in an action-reaction pair. So we must have a look and see what is actually going on when this situation occurs. Primarily, the action and reaction forces are acting on different objects, and that's why they don't cancel out. Our cancelling only occurs when we have two forces acting on the same object, and that's when they can balance or cancel one another out. I guess the primary examples, as I mentioned, are rockets and missiles, which have a huge amount of force which is driven from one side of them, which projects those projectiles in the opposite direction. Jet engines are the same, and all of these rely on the action-reaction force pair principles. And so does the firing of bullets and shells from different guns. So as you can see from over here, if I were to draw in the little bullet here, the bullet is going to come in this direction, and that's going to be a result of acceleration along the muzzle of the gun. But often guns will have a recoil, and that recoil is going to go back in the opposite direction. And of course, the larger the gun, or the larger the shell in particular, so this will be a mass, and the force is being applied to that mass, but you've got an equal and opposite force that's being applied backwards in the opposite direction, and as a consequence of that, you often get recoil, this phenomenon that we know as recoil. So it's probably worth at this point having a little bit of a comparison of the three laws that we've been looking at over the past couple of videos. So we've looked at Newton's first law, we've looked at Newton's second law, and Newton's third law. When we break these down, we find that in Newton's first law, there may be hundreds and hundreds of forces, but ultimately there is zero net force, no newtons. And so as a consequence of that, there is acceleration is zero. And there's no change in velocity. So either the object stays at rest or it continues at a constant velocity. Because in the second one we have one force, so therefore we have a value, we have greater than 0 newtons, and so therefore the acceleration is not equal to 0. It may be deceleration, it may be slowing an object down, so it may be less than 0, or it may be greater than 0, and therefore speeding an object up. We use F equals ma to do our calculations, or find the acceleration by dividing the force by the mass. And then in the third situation, we have two forces, and they are equal and opposite. So we have an action and a reaction pair that are exerting equal and opposite forces on two different objects, and so that's why they are a pair. The important thing is that in the first one we have no change in velocity. In the second one, the acceleration is equal to the force divided by the mass, and in the third one, A is dependent on the mass, and there may be two different accelerations. So we are going to need to to try and look at how these affect one another in different ways. One other way of thinking about that is to very simply look at, say, a car and a truck that have a head-on collision. So this is the truck and this is the car. The thing that's important to remember is that the force, when the two strike each other, the forces will be equal and opposite. So that if the force of the collision is, for example, let's say the force is equal to 1,000 newtons, oops, make that 1,000 newtons, then that will be an equal and opposite force. So that the truck will apply 1,000 newtons to the car and the car will apply 1,000 newtons to the truck. Now, quite obviously, because the mass of the car is going to be so much less, the acceleration of the car in the other direction is going to be much greater. So it's not so much the fact that the forces are identical, it's the fact that the mass of A may not be equal to the mass of B. That means we would end up with a situation where the truck would suffer significantly less damage than the car. In fact, the truck may continue to just be slowed down as it continues in the same direction, whereas the car might actually end up crumpled and start to actually move in that opposite direction. So we've got a couple of examples here to look at. A person sitting in a car traveling at a constant speed would be an example of Newton's first law. A golf club striking a golf ball on a tee, so what's happening to that golf ball, be an example of acceleration due to the application of a force. And then a rocket engine during takeoff, that's a couple that we can look at of an action-reaction pair. So here's a question. In space, an astronaut pushes on another astronaut with a force of 80 newtons. Identify the magnitude of the reaction force in this case. Well, clearly, if this is regarded as the action force, then the reaction force must also be equal to 80 newtons, but in the opposite direction. Now, we're not given a direction here, so we're just told that one astronaut pushes on another, so they're each going to apply 80 newtons to each other. Our second question here is to explain why the second astronaut could have a higher acceleration than the first astronaut. Well, the force of one is equal to the force of the other. So the two are experiencing the same force. So because we know the acceleration is F on m, then the two accelerations are going to be a consequence of the difference in the mass. So these two may be equal, but the only reason that A1 and A2 would be equal is if M1 equals M2, then A1 equals A2. But if the second astronaut, if M2 is less than M1, then the acceleration of 2 will be greater than the acceleration of 1. And if it's hard for you to follow these things, put some numbers in. So if we said this was 80 newtons, and we said that the second astronaut maybe was just 40 kilograms, and the first astronaut was 80 kilograms, to make our numbers nice and easy, then the second astronaut is getting 80 over 40, which is 2 meters per second squared, whereas the first one is going to be 80 over 80, which is 1 meter per second squared. This is why these numbers can be different, and it's worth doing a few questions just to make sure you understand how these work. Thanks for watching.